Welcome to tutorial number 4 on the challenges of fusion. My name is Chris Warrick, the Head of Communications for the UK Atomic Energy Authority. I'm going to take you through, in some simple terms, some of the major challenges that stand between us and a future fusion power station. I'd like to thank again the graduates who've put these slides together for all 6 of our tutorials. We hope you've enjoyed watching them either live or now on Nucleus and on YouTube. We've certainly enjoyed putting them together, and we hope you've got something out of them and understand a bit more about the fascinating world of fusion. So this talk is about the challenges that stand between us and putting a fusion power station on the grid. There are 6 main challenges. Many of you at the authority will have seen this figure before, because we actually do a work into a lot of these particular challenges. The first is in creating the fusion reaction at all. We need extreme conditions in our plasma, our very hot gas of fuels, to do that. We need to heat up to 150 million degrees. Critically, we need to get a plasma to burn. That does not mean to say it's on fire at all. Burning means that it is largely self-heating. It is sustained enough that the energy produced from fusion, in particular in the helium, keeps the plasma hot enough and sustains it. We need to sustain a magnetic field to hold that in place, and we'll talk a little bit about that in this talk. We'll also talk about the challenges for materials, which is truly huge and very diverse. We need materials that can cope with high heat loads, materials that are resistant to holding tritium, materials that are resistant to the damage and irradiation caused by neutrons, and we'll touch a little bit on that. Innovative engineering will come in a future talk about how to put a fusion power station together. That will come in talk number 5, as will fuel handling. We need to look at breeding and using the tritium fuel in particular, which is much more difficult to handle than the deuterium that we use. I will also touch in this talk on how we exhaust our excess heat from the plasma. We produce too much heat in there, and we need to get rid of the excess, and we need to get rid of the helium once it's cold. And I will also talk a little bit about robotic maintenance and the huge challenges that we face there. These are some of the really practical technology and engineering issues that stand between us and putting a fusion power station on the grid. And I will touch on each of these in turn. So to emphasize, how can we hold a burning plasma for extended periods? Again, a burning plasma is a plasma that is sustained and heated by the action of the plasma itself largely. That is from the helium that we produce, can sustain and keep that plasma at fusion type conditions, but we need to work out how we can produce long-lived magnetic fields for that to happen. So we'll talk a little bit about that. What we do with that heat, the excess heat that we no longer need, how do we get rid of that? That requires the plasma to touch material surfaces. How can we deal with that? What generally do we want our materials to do to survive in this environment? And there are various issues around that, so we'll touch on those very, very briefly. And how can we protect humans? We cannot send humans going into the machine. This is a radioactive process, and the interior of the fusion device is radioactive, mildly in the case of jet, but more so in the case of a future power station. We need to devise remote handling techniques that work both inside and immediately on the outside of those devices, so that we are not caught out with a problem that we can't fix robotically. So we'll have a quick look at all of those in just a few slides on each. The first on a burning plasma, we require our plasmas, in the case of a burning plasma, we require them to last for potentially continuously, but certainly many hours at a time. And if we contrast that with what jet can do at the minute, jet can only operate for 30 to 40 seconds, maybe a minute at most. One of the reasons, and there are a few, is that jet has conventional, as we call them, copper magnets. Copper coils heat up. In a previous tutorial, we talked about the action of the electrons flowing through a material and the fact that they will collide with the atoms and heat that material up, and that is wasted energy. So because our copper coils on jet heat up, if we run for really long pulses, our coils start to get too hot and won't run any longer. So there is a material, there are a suite of materials, and particular ceramics in particular, that are so-called superconductors. Superconductors are materials that exhibit zero resistance. There is an internal rearrangement of the particles that essentially means the electrons can flow completely freely, not colliding with anything, and exhibiting essentially zero resistance. So this is a real game changer for fusion. If you can make your magnetic coils out of superconducting materials, then you have no resistance, they don't heat up. And actually, once you've set the current running around them from your power supply, you can switch off that power supply and the current will continue to run. This means it's much, much more efficient. You're not constantly driving current around the coils to make the magnetic field. You start that current off and then just let it go. And essentially, you're getting your magnetic field for free, except these superconductors are required to get very cold before they're superconducting. So you do need to think about the energy you use in cryogenically cooling the coils. We'll come to that in a second. But these superconductors we know are going to be very, very important to hold plasmas and hold burning plasmas for long periods of time and make a future power station economic. Superconductors are around and have been known about for many, many decades. They typically are exhibited in quite rare metals and ceramics and alloys. They can create high fields, and they can do that continuously without heating up, as I said, without exhibiting any resistance. And on the left here is some superconducting strand, a picture of some superconducting strand. All of the conductors in there are superconducting if we can get down to the really low temperatures we need. And on the right are some coils being wound for ITER. ITER is the next machine along from JET, will use superconducting coils. I'll come on to that in a second. They do require very, very cold conditions. This is the disadvantage. We actually need, for the superconductors we're going to use on ITER and indeed in other fusion experiments at the minute running with superconductors, we need the temperatures to get down to near absolute zero. In the case of the superconductors we know about at the minute, then that is at liquid helium temperatures. Liquid helium liquefies at just 4 degrees above absolute zero. That's minus 269 degrees centigrade. Minus 273 degrees centigrade is the lowest temperature anything can get to. So we're right down at the very bottom. These particular materials are superconducting only when we cool them at that kind of temperature. And liquid helium we have to put quite a lot of energy into manufacturing that. At the top right is a picture of a cryo plant. We have a big cryo plant producing liquid helium. And indeed using liquid nitrogen as well, and we have deliveries of liquid nitrogen to Culham. Our cryo plant does not do this for the magnetic coils. We have copper coils on JET, but we do use it to supercool some detectors and other uses, especially on JET. And indeed, we're looking to put a cryo plant and cryo pumps into MAST as well as we upgrade the MAST machine. So we can take that helium, heat it down to these crazy cold temperatures, which requires energy, of course. And on the left, you can see liquid helium has absolutely fascinating physical properties, liquid helium, for all sorts of reasons. But once we can cool particular coils down to those kind of liquid helium temperatures, they will be superconducting, and this will be a big, big technology that needs to get used in ITER and future fusion power stations to make them economic. We need much less energy to drive the cryogenic plant than we would use if we used conventional coils. So it certainly does save us an awful lot and start to turn the economics in our favor. We talked about these being vital on ITER. There is a picture on the right of the superconducting coil set on ITER with a person to give you some sense of scale. These are huge. In the case of ITER, these are niobium tin, and these are the biggest superconducting magnets that the world has ever made. These are absolutely huge. These are 12 to 14 meters high. And indeed, some of them have already been wound and tested. So this really is pushing the boundaries of what we can do. But absolutely vital. ITER will produce 500 megawatts out, but its requirement for magnetic fields is much, much less than on JET. So we actually will produce more power out of ITER than we put in. And ITER will start to demonstrate some kind of gain towards a fusion power station of the future, which will exhibit significant gain to make it economic. On the picture on the left is a picture of JT60, which is a large, recently upgraded tokamak in Japan, similar size and scale to JET. It doesn't have remote handling of deuterium, but it does now have superconducting coils. So JT60 will do a lot of work in preparing the way for operating the coils on ITER. Understanding how they work there is very, very important. So that's superconducting coils, and they are really important, not just in fusion, but in other industries. We're going to look a little bit now at how we get rid of that excess heat we talked about. Here is a picture of a plasma on MAST. We also, of course, produce very high temperature plasmas in jet. There is the plasma. We are magnetically confining it, getting it as hot as we can in the interior so that fusion conditions prevail and we start to see fusion. And we start to produce neutrons from that fusion reaction. But we almost produce too much heat for our own good, and we need to excess that. In addition, the helium that we produce in there that stays in the plasma, we talked about that burning plasma. The helium, as it cools and collides with the incoming deuterium and tritium, helps to heat and self-heat the plasma, and that can be a very powerful mechanism in much larger power plant scale devices, and that's certainly what we assume in future devices, that it will largely be self-heated by the helium. But once it's cold, it's a contaminant. It's an impurity we need to exhaust out, so we need to find a way of getting rid of it. You'll note in the bottom of MAST, and many of you will have seen these pictures before, the very bottom that we're focusing on there is where we deliberately cross the edges of the plasma, and two plasma streams then will penetrate into what we call a divertor region, where we divert the plasma streams and we pump away the excess heat and particles that come out through the edges of the plasma. Those divertors have to withstand some kind of heat load. And for some decades now, we've looked at this problem and realized that it is quite a big issue. Materials deal with heat loads all the time, but it's how much heat load they deal with that gives us the kind of headaches we've got with fusion. And then I will talk a little bit about the potential solutions as well. There is a combustion engine that many of us have in our cars. That has to deal with heat loads as the cylinders move around. We actively cool an engine with water and with a combination of water and air. But we do, the materials in the engine do get up to heat loads of something up towards 100 kilowatts per square meter. These are perfectly able for standard, relatively standard materials to deal with. We're much cleverer at that now, and indeed a car engine, if well looked after, could last for up to 20 years, many hundreds of thousands of miles potentially. So that's the kind of technology we know about and we can deal with. If you go up again in scale, you're getting to something that's much more difficult to deal with. So a spaceship re-entering the Earth's atmosphere, this is a picture of the space shuttle, but you could equally look at the Soyuz capsule bringing astronauts back from the ISS, has to withstand just for 20 minutes or so pretty extreme heat loads, up to a megawatt or two, or maybe up to 5 megawatts per square meter. Really difficult to do that, even for that 20 minutes, and that requires clever ceramics and clever design to make sure that that happens properly. And that is the kind of power levels we exhibit on a fusion divertor. We'll talk about that again in a second. And beyond that, we're up to where we deliberately deform and change materials around. An arc welder deliberately melts and reforms joints. And that is not where we want to get to. But with fusion, we're currently in the middle and in a region where we have to be very, very careful about the materials we choose and how often we'll have to replace them. So that's the kind of range of heat fluxes materials typically have to deal with in particular scenarios today. So here is a still image of a plasma in jet. Jet has a divertor at the bottom. You can clearly see the two streams of plasma striking at the very bottom into two grooves of the divertor region. And if you look at an empty picture of the vessel, those grooves become much, much more obvious. On the left there, you can see at the bottom where we've got angle plates in the middle and two troughs essentially that run all the way around the machine. We magnetically steer and cross the two edges of the plasma, and our two plasma streams move into that region and strike those plates, those special plates at the very bottom of jet. Those plates are made of tungsten, one of the hardest wearing materials we know about. And we know that in a fusion, in a jet plasma, and indeed in a future fusion power station, the helium that we make, as well as the deuterium and tritium, will make its way to the edge of the plasma, be swept down to this region and pumped away. Underneath there on jet is a cryopump, a very cold surface that essentially condenses and sucks anything away that touches it. The kind of power loadings we know about and can predict for future power stations are of the order spaceship reentrant power levels, a few megawatts per square meter. But in the case of for us, we would have to withstand that in jet just for a few tens of seconds, but in ITER an hour or two, in a power station of the future, days and days and weeks, years and years, potentially up to 40 years. And no material will cope with that. Tungsten will do a pretty good job, but within a few years, we predict that we'll need to change the tungsten around. That requires getting remote handling in, changing the tiles, and this is all affecting the economics. So we know there's an issue coming. Tungsten can help us, but we know that we need to try and do better. And what we're going to do on the upgrade to MAST is something called the Super-X Divertor. You may well have heard of this. This is a clever divertor configuration, and there is a picture of the divertor region in MAST. Here is the upgrade to MAST, currently finishing off final commissioning and hoping to start running later this year. And MAST has a diverter top and bottom, so that helps you straight away in spreading and sharing the load more evenly. We deliberately magnetically steer the plasma streams much, much further into those private regions at the top and bottom. That acts to do two things. First of all, by doing that, we deliberately spread out the power loading much more across the plates. The plates are much bigger here than they are in jet. And by it traveling further, it actively cools itself so that by the time we impact on those plates, we expect, and we don't know this for sure until we run the experiments, but we expect to be up to an order of magnitude 10 down from what we exhibit inside jet. That gets us down to the kind of power levels found in a car engine, stuff that we're much more used to dealing with. If that works, and there is a big if because research science is like this, but if that works, that's a real game changer for fusion. Here is a diverter design where the power loading is much less. You don't have to get in as often to change the tiles around. That improves the economics and the efficiency and the viability of a future power station. So this is a really big deal, and one of the biggest things, if not the biggest thing, that that MAST will look at. ITER won't have a Super-X diverter, but indeed power plant designs beyond could easily do that, depending on the results we get from MAST upgrade. So you can see that exhausting the heat is a big issue. That's where we certainly need heat-resistant materials. We also need materials to do many other things and exhibit certain properties to minimize the damage caused by the very harsh environment of a fusion power station. Our materials research facility is looking into all sorts of materials and just starting to do that work, and will be absolutely key, working with universities as well, to find and develop cleverer materials for our uses. So what are the particular challenges here? Here is a reminder of the fusion reaction, deuterium and tritium sticking together to form helium and a neutron. The helium stays in, as we just discussed, and we need to exhaust it out when it gets cold through the diverter. The neutron flies out. That is what captures most of the fusion energy, 80%. That will fly out. It has no charge. It doesn't care. There's a magnetic field there, and it will penetrate into the material structural surfaces of the fusion power station, the steels or whatever we use to make the structure of the power station out of. There are several issues there. Here is a neutron, and here is a standard metal atom. It would have actually more protons and neutrons than that, but a heavier atom of some kind of structural material. The first thing a neutron might do, most of them will just pass past these atoms and start to slow down through collisions and give up their heat to the surfaces. We'll come on to how that works in the next talk. But it can cause damage and it can cause irradiation. What a neutron might do is this. It might get absorbed into a particular metal atom. And in some cases, that will give radiation out. So let me just give you an example of that. If we use Inconel, which is often what we use for certainly for MAST and jet, or other types of steel, they contain some elements, some amounts of cobalt. Most of these materials do. Cobalt has 59 protons and neutrons and is utterly benign. But if it captures and picks up a neutron, it turns into cobalt-60. It's gained an extra nucleon. It's gained a neutron. It's now an isotope of cobalt, and cobalt-60 is a radiation emitter. Whatever we make our power station out of, it is unlikely we'll find any material mix that will be immune to this picking up of neutrons and this radiation production. But it is in our gift, if we're clever and we can find the right materials, to find materials that don't get too active, or that if they do, the activation dies off quite quickly. This is less long-lived than activation from fission, but we wish to find materials that would minimize that activation right down. Impossible really to consider no irradiation, but certainly minimize that radiation. The second issue, and here is a group of metal atoms, each of course containing all those protons and neutrons we just spoke about. The other thing a neutron might do, because they're very, very fast, 10 times faster than the neutrons from standard nuclear fission, is that it can easily do this. It won't do it all the time, but we know that a neutron can knock an atom out of place. Metal atoms are very carefully arranged in a very structured and uniform structure, just like this, where they're all lodged on top of each other and next to each other, very closely bound. That's what makes a metal very strong. By the action of the neutrons, we'll start to knock atoms out of the way, what we call displacements, and we'll end up with a weakened metal structure. Again, if we can find materials that are particularly resistant to these particular neutrons, that will help us hugely in devising structural materials that will last for the 40 or 50 years we need them to in the environment of these very fast neutrons. Finally, the very first wall materials, those tiles that we saw on JET, particularly are prone to absorbing fuel from the plasma. We have deuterium and we have tritium. We don't really mind too much if it absorbs deuterium, that's neither here nor there. If they absorb tritium too much, they become really quite active in their own right. Tritium is a radioactive gas, it's a radioactive isotope of hydrogen, has a decay time of about 10 years, half disappears in 10 years, but we just don't want tritium fuel in the tiles, in the plant itself. We want it fusing in the plasma. Machines like JET, and indeed when we were looking decades ago to power plants, we wanted to use carbon. Carbon was a very good first wall material for many reasons, but its Achilles heel was its ability to suck in tritium and hold it, and we didn't want that to be the case. This is why we chose 10 years ago now to change the whole wall structure on JET to beryllium, which is much more immune to absorbing that tritium, and tungsten at the very bottom in the divertor. So we're actively looking for materials that resist absorption of tritium because we don't want to activate the machine too much. And our materials research facility is looking into these materials issues, in particular the irradiation and damage. We can take structural samples that have been irradiated by fusion energy neutrons in other facilities. The MRF gives us the ability on a very small scale to test how weakened they have become. How can we do that? We can take really very active samples, but we're not a licensed site, of course, at Culham, neither would we wish to be ever. We can do that because we only can take in very small material size samples of these very active materials. So we are in the middle towards the high active range of materials. Low activity structural work and materials testing can go on in universities. We sort of stand in the middle ground. The very high active end is where Sellafield can test very big components. So there's an overlap here with the MRF with the fission industry, but they can look at candidate fusion materials, and we really hope the MRF will play a role in developing these materials in the future. Finally, we're just going to talk very quickly about remote handling. We have a remote handling system in JET. JET is unique in the world, in tokamaks, of having a remote handling system. And we've been able to demonstrate doing pretty much anything in vessel, changing tiles, aligning things, lifting in new equipment, even hoovering up after themselves. The boom inside JET does absolutely amazing things. On the left, you can see the boom coming in, and it works very often in tandem with a second boom, bringing in fresh equipment, taking out old stuff to be stored and monitored. But in future fusion power stations, we'll need even cleverer robotics to look on the outside of the machine as well as the inside. Here is a better picture of the boom inside JET. On the right-hand side, you can see it very much mimics a pair of arms. If you've never seen this, when we certainly get back to site, we'll try and do a show and tell where we can show off the remote handling gear in action. It is quite amazing. There are operators 50 meters away operating the main end of the boom, and the real boom inside the machine will do exactly as they're telling it to do. So they can do very complex tasks with this remote handling system. But we do not use that on the outside of the machine. Remote handling systems on ITER will have to test how we can fix things on the outside of the machine as well as the inside, because in ITER and future fusion power stations, the activation levels will be higher. We're going to need to work remotely, much wider range. The other issue is that the radiation, certainly the radiation caused by neutrons, can damage standard cameras. If we're going to rely on a standard set of cameras to look inside and control the remote handling, this is what happens to cameras when they're subject to intense fusion radiation. They start to white out. So we are developing, and RACE is developing, really clever virtual reality systems. They already use virtual reality a lot in operating in jet, but trying to devise control systems that can link a robot with the users in as absolutely a seamless way as possible, cutting out any kind of analog signals and camera views, and using virtual reality in almost all regards. So some really clever stuff up at RACE, looking at what future systems might look like, helping with industry to design systems for ITER and looking beyond to the first power stations. And it is really a genuinely industry leader. It's grown hugely over the last 3 years, RACE. Starting now, if you can look in the bottom left, to link up industrial type robots. This is a KUKA that will be on the line at a car factory with a fusion environment, so that we can bring this much more mainstream, devise these clever control systems, but devise robotic systems with industry that can work in ITER and future fusion power stations. So finally, very quick whistle stop through some of the major technology issues that we have to face. We have to think about superconducting magnets. These are absolutely essential for future fusion power production, so that we can magnetically sustain a burning plasma efficiently and economically. How can we get that heat out that we do need to do, and get rid of the helium as well? That requires this divertor to be very carefully designed. Materials that are needed to survive irradiation from neutrons, damage from neutrons, tritium retention, and also extreme heat loadings, all in different parts of the machine. Lots and lots of material issues we need to face. And remote handling systems that minimize and actually rule out completely human interaction with the machine to do maintenance and upgrade work on it. All of these are technology and engineering issues that we need to face. It's what makes fusion absolutely fascinating and a massive challenge to get it on the grid. I hope you've enjoyed that talk. It's given you at least a glimpse into what the real challenges are. A couple more challenges will be looked at in the next talk, tutorial 5, how a fusion power plant will work and what we need to think about to put that together. So do tune in for that as well. And finally, if you need to find out more from us, here are our social media feeds. Follow at UKAEA Official on all social media feeds that you can think of, bar a few. On our websites that you can see there, Eurofusion being the website for the European Fusion Programme, in particular looking after JET, and our own fusion website, ccfe.ukaea.uk. Thanks ever so much for listening. I hope you've enjoyed all the tutorials, and I hope you found them useful and learned something from them. Many thanks. Bye-bye.